Hello everyone! In the study of Task 1, we have collectively learned about the basic components of the power system and power grid, the fundamental concepts and types of power plants and substations, as well as the main parameters of electrical equipment. In particular, we have understood the basic concepts of the power system and recognized the impact of power system stability and operational reliability on national economic life. We will now study the content of this section together. The operational modes of the neutral point in the power system. Through this lesson, you are required to master the working characteristics of various operational modes of the neutral point in the power system and develop the ability to analyze and judge the various operational modes of the neutral point in the power system. This aims to cultivate a good awareness of safe electricity usage and improve analytical and judgment skills. The key point of this lesson is the working characteristics of various operational modes of the neutral point in the power system. The difficulty lies in understanding the magnitude and phase relationship of voltage and current during single-phase grounding faults under various operational modes of the neutral point in the power system. So, what is the neutral point? First, let's watch a video together to understand the basic concepts and manifestations of the operational modes of the neutral point. The neutral point grounding method refers to the electrical connection method between the neutral point of a three-phase AC power system and the Earth. It involves the safety, reliability, and economy of the power grid, while directly affecting the selection of insulation levels for system equipment, voltage levels, lightning protection methods, and communication interference, among others. Generally speaking, the neutral point grounding method of the power grid, that is, the neutral point grounding method of transformers at various voltage levels in substations, is divided into effective neutral point grounding and non-effective neutral point grounding. Power grids of 110 kV and above in China generally adopt the large current grounding method, i.e. the effective neutral point grounding method. D-distribution networks of 635 kV generally adopt the small current grounding method, i.e. the non-effective neutral point grounding method. The non-effective neutral point grounding method can mainly be divided into the following three types: ungrounded, grounded via arc suppression coil, and grounded via resistor. Throughout the video, we have gained a preliminary understanding of the content to be studied in this section. What is the neutral point? What are the operational modes of the neutral point in the basic electrical engineering course? We were introduced to the concept of the neutral point. It generally refers to the point where one end of each phase of the power supply or load is connected together in a star configuration during the operation of generators and transformers. This point is the neutral point. The operational modes of the neutral point refer to its grounding methods, which can be divided into the ungrounded neutral point operational mode, the arc suppression coil grounded neutral point operational mode, and the directly grounded neutral point operational mode. In the field, technical personnel often refer to the first two operational modes as small ground fault current systems, and the third directly grounded neutral point operational mode as a large ground fault current system. Why analyze the various operational modes of the neutral point in the power system? Because different operational modes affect the safety and reliability of the power grid, equipment insulation, communication interference, as well as relay protection and its economy. Next, we will analyze the characteristics of the three neutral point operational modes together. First, as shown in figure 2:1, it is the circuit diagram and vector diagram of the ungrounded neutral point operational mode. From the figure, we can clearly see that C represents the distributed capacitance between each phase and the ground. Air is the insulating medium. And to facilitate analysis and discussion, we uniformly assume that the three-phase system is symmetrical. The distributed capacitance to ground is represented by concentrated capacitance. The capacitance between phases is not considered here after complete transposition of the conductors. The capacitance to ground of each phase is equal. At this time, the three-phase system is symmetrical and the three-phase voltages are symmetrical. Their vector sum is 0. Since the capacitance to ground of each phase is equal,
The capacitance to ground of each phase is also symmetrical. Thus, their vector sum is also zero. Through rigorous, detailed, and careful analysis, following conclusions can be drawn. During normal operation, no continuous capacitive current flows through the ground, and the potential of the neutral point to the ground is also zero. When a single phase fault occurs, we still take phase C as an example for analysis of the changes in voltage and current. First, analyze the voltage changes. The voltage of the non-fault phases increases to the line voltage, i.e., increases to how many times the original? Lu to 3 times, and the voltage to ground of the fault phase drops to 0. Then let's look at the current changes. It can be seen that the capacitive current flowing through the grounding point is how many times the normal capacitive current to ground per phase. 3 times. Finally, we can draw the following conclusions. The voltage to ground of the faulty phase decreases to 0. The voltage to ground of the non-faulty phases increases to the line voltage. The voltage of the neutral point to the ground increases to the phase voltage. The phase to ground voltage, neutral point voltage, and line voltage remain unchanged. Thus, the three-phase system remains symmetrical, allowing the power system to continue operating for how long? 2 hours. This provides time for staff to eliminate the fault while ensuring power supply reliability for users. This is the advantage of the ungrounded neutral point operational mode. The capacitive current flowing through the grounding point is 3 times the normal capacitive current to ground per phase. It can be seen that due to the increase in current, overvoltage occurs at the grounding point, producing an electric arc. As we all know, electric arcs are highly hazardous. They threaten equipment and may even cause 3-phase or 2-phase short circuits, affecting the safety and stability of the power system. This is the disadvantage of the ungrounded neutral point operational mode. Let us take a look at the second operational mode, the arc suppression coil grounded neutral point system. Why adopt the arc suppression coil grounded neutral point system? When analyzing the first operational mode, we mentioned that when a grounding fault occurs in an ungrounded neutral power grid, it can still operate continuously for 2 hours. However, when the grounding current value is too large, it can produce a sustained electric arc, threatening our equipment and even causing 3-phase or 2-phase short circuits. Can the arc suppression coil grounded neutral point system avoid these problems? Let us analyze it together now.
As shown in Figure 2.3, when the system operates normally, the potential of the neutral point to the ground is 0. No current flows through the arc suppression coil, and the capacitive current flowing through the ground is also 0, which is consistent with the ungrounded neutral system at this time. When a single-phase grounding fault occurs, we see that the neutral point potential rises to the phase voltage. What appears in the arc suppression coil? Inductive current IL. It differs from the capacitive current by 180 degrees in phase. The phase difference between them, the current flowing through the grounding point, is 0. The phasor sum of the inductive current and capacitive current is 0, canceling each other out. Thus, we use the inductive current to weaken the capacitive current, reducing the current, and avoiding the generation of overvoltage, thereby suppressing what? The formation of electric arcs. This is the electric arc we do not wish to exist. By weakening it with the inductive current, we suppress it. Depending on the degree of compensation of the capacitive current by the inductive current of the arc suppression coil.
We have 3 compensation methods. Different compensation methods also have certain impacts on the safe, stable, and reliable operation of the power system. Let we look at them respectively. The first compensation method, full compensation. When the capacitive current and inductive current are equal, the current at the grounding point is 0. But the perspective of arc suppression, full compensation is best. But is this the case in actual work in practice? We do not adopt this compensation method because it may produce series resonance in overvoltage that endangers the insulation of the power grid. The second compensation method, overcompensation, that is, capacitive current, is less than the inductive current. There is still excess inductive current at the grounding point. Overcompensation can avoid the generation of resonant overvolt. Therefore, this compensation method is widely used. The third compensation method, undercompensation. The capacitive current is greater than the inductive current at this time. There is uncompensated capacitive current at the grounding point. The undercompensation method is rarely used because it often easily develops into full compensation. Throughout the above analysis, we can conclude the voltage to ground of the faulty phase becomes zero. The voltage to ground of the non-faulty phases increases dilute 3 times the original, i.e. the line voltage. The voltage change is consistent with the ungrounded neutral system. The insulation level to ground of the system phases should be considered according to the line voltage at this time, enabling the system to withstand the highest voltage generated. This increases the investment cost, affecting the economic level. The phase to ground voltage, neutral point voltage, and line voltage remain unchanged. The 3-phase system remains symmetrical, allowing our system to continue operating for 2 hours. Supply reliability is improved. The capacitive current flowing through the grounding point is weakened by the compensation method. The safety and stability of the system are also improved. Having studied 2 operational modes, let's now analyze the 3rd operational mode, the directly grounded neutral point system, when a single phase direct grounding fault occurs. We still take phase C as an example to see how the voltage changes. The voltage of the grounded phase decreases to 0. The first 2 operational modes also decrease to 0, which is consistent. The voltage of the non-faulty phases remains unchanged. Still, the phase voltage in the first 2 operational modes we introduced, it had increased to dilute 3 times the original, i.e. the line voltage. How should the insulation level be considered here? It should be considered according to the phase voltage at this time. It is economically lower than the consideration of the first 2. The voltage of the neutral point to the ground remains unchanged, still 0. Let us look at the current changes. What happens at this time? The short circuit current instantly becomes the short circuit current, which is highly hazardous. It is necessary to install relay protection devices at this time. When a grounding fault occurs, the protection device trips and acts, disconnecting the faulty line POTI. Supply reliability is low. Of course, it simultaneously avoids the sustained burning of the electric arc at the grounding point due to its tripping and power stoppage. It is thus inferior to the previous 2 operational modes, because the previous 2 operational modes can operate for 2 hours, providing sufficient time for staff to eliminate the fault. What are the advantages of the directly grounded neutral point system? First, it does not require additional equipment to eliminate the electric arc. Second, it reduces the insulation of the power grid to the ground, does not produce overvoltage, and reduces the insulation level of equipment by 20%, saving cost. What are its disadvantages? First, power supply reliability is reduced. However, we can improve power supply reliability by installing automatic reclosing devices and adding backup power sources. Second, the current is very large, and the unidirectional magnetic field causes interference to weak currents. Therefore, we can adopt measures such as grounding the neutral point by a reactor or grounding only part of the neutral points for improvement. In this section, we introduce the 3 operational modes of the neutral point. In the power system, we analyze the operational characteristics of the 3 modes respectively, especially the impact of voltage and current changes on the power system, as well as their respective advantages and disadvantages. Students can consider the following questions after class. What are the operational modes of the power system source neutral point? What is a small ground fault current system? What is a large ground fault current system? Why is it said that the full compensation method using arc suppression coil grounding is not advisable? Describe the consequences of a single phase grounding fault in a directly grounded neutral point system and the measures to improve power supply reliability. This is the content of this lesson. Thank you for listening.